Yes, good afternoon dear students. Today our topic of discussion is current transformer, its equivalent circuit and how to write its phasor diagram. First of all, we need to understand why we need a current transformer. See, whenever we have high power requirement, high power in the sense where we use high power is used in the substations, okay, so there we need current transformer. For example, we are getting an input current of 3000 ampere, so with a normal transformer it is not possible to receive a huge amount of current or to measure that huge amount of current with the help of a normal instruments. So we are using a current transformer to measure that current. Input, it will be having a higher value of current, and that high value we are converting it into low value with the help of a CT, and then we are measuring the current. So let us see the circuit diagram of a current transformer. Well, this is the circuit diagram of a current transformer. This is the line and this is the neutral of a substation. So what we are doing here, we are connecting a current transformer in series with the line. So the input we are getting around 3000 ampere of current, and this is the supply voltage. Vs is the supply voltage, and this is the core of a transformer. This is the primary winding and this is the secondary winding, and here we have connected an ammeter in the secondary. Now if you observe here in the primary, we are using only one term, that is N1 is equal to 1, okay, and in N2 we are having many number of terms, that is N2 is very much greater than N1. As the number of terms increases, the value of current decreases, and as the number of turn becomes minimum, the value of current will become maximum. So here it can allow 3000 ampere of current to flow through it, and this is a load. Now if we consider the transformation ratio, that is V2 by V1 is equal to N2 by N1, which is equal to I1 by I2, and if you consider these two equations, you can say that current is inversely proportional to the number of turns. As I said, as the number of turns increases, the value of current decreases. So if I want to find the value of I2, that is N1 by N2 into I1. So now let us consider the equivalent circuit of a CT, okay, or generally we consider a general equivalent circuit of a transformer which is having an inductive load. So this is the equivalent circuit of a transformer, okay. So this is having a supply of V1 volts, that is the input supply, and we are having a primary resistor R1, primary reactance X1, and this is the primary winding, and we are having a core loss component, that is RC, and a magnetizing component XM, okay. The current flowing through RC is IC, and the current which is flowing through XM is IM, and the overall current which is coming here is I0, which is called as no load component, okay. So this is with respect to the primary, and the current flowing through the primary is current I1, and the EMF induced in the primary winding is E1. Here coming on to the secondary side, that is the EMF induced here is E2, and we are having a resistance of R2, okay, and reactance X2, and this is the load ZL, and the voltage here is V2, okay. Now to write the equivalent circuit or to write the phasor diagram from this equivalent circuit, how many parameters are there? Means totally in this equivalent circuit we are having 15 parameters. So we should represent all these 15 parameters in the phasor diagram. So in the secondary side, what are the parameters we have? We have E2, I2, and this is the drop across the secondary resistance, that is I2 R2, drop across the reactance I2 X2. So all these parameters and V2. So all these parameters we should represent in the phasor diagram. Next, this flux phi, this is common for both primary winding as well as the secondary winding. So this is one parameter. Now when it comes to the primary side, we have E1, I2 dash, IM, IC, I0, I1X1, I1R1, I1 and P1. See, similarly I1R1 is a drop across resistor R1, I1X1 is a drop across the reactance X1, and this is I2 dash, which is equal to minus K times of I2. Here K represents the turns ratio, which is equal to N2 by N. Okay, this is minus K times of I2. Now let us start writing the phasor diagram for this. We should consider a reference, means that reference should be common for both primary winding as well as the secondary winding. Now which is the parameter in the equivalent circuit which is common for both primary as well as secondary, that is this flux is common for both primary as well as secondary. So what I will be doing, I will be considering this flux as a reference. Okay. Now let us consider the secondary end. Okay. If I apply KVL to this part, what happens? V2 is equal to E2 minus I2 R2 minus I2 X2. This is the expression. Now here, if I observe, I am not having any equation relating to phi here. So what I will be doing, I will consider the Lenz's law. Okay. That is E2 is equal to minus d phi by dt. What is this phi? Phi is nothing but phi n sine of omega t. Okay. So if I substitute here, what I will be getting? E2 is equal to minus of phi omega n cos of omega t. If I convert this cos in terms of sine, that is E2 will be equal to omega times phi n sine of omega t minus pi by 2. If this sine omega t minus pi by 2 becomes 1, then what happens? This E2 will become Em, that is E2 is equal to Em sine of omega t minus pi by 2. Now this flux and this E2 are having a relation, that is this E2 is lagging by an angle of 90 degree with respect to the flux phi. That is from here I can write this as E2. Okay, and this is lagging by an angle of 90 degree. Now I have completed this part and I have completed this part. Okay, E2. Now I2, where I should get this I2? I2 lags E2. Okay, so if E2 is here, the lagging current, it should be somewhere here, and this is my current I2. This I2 is lagging by E2 at some angle. Okay. Now even I2 I have represented it. Next, E2 I have completed it. I have I2. Next, I need I2 R2. This I2 R2, that is the drop across the resistor R2. Observe the phasor diagram here. If current I2 is flowing in this direction, then even I2 R2 should also be in the same direction, because it is a resistor and it will be in phase with the current. So I2 R2 phasor will also come here, but it will be in the opposite direction like this. Okay, and it is in summation with this E2. This I2 R2 is in summation with this E2. So this vector, what I will be doing, the same vector I will bring it and I will replace it here. Okay, so this will be my I2 R2. Are you getting it? I2 is in this phase, so I2 R2 should be in this phase, the vector, and it is minus I2 R2. Okay, so this phase will change its direction here, and the same vector I am shifting it here. So these two are in parallel. Now next we have minus I2 X2. So this is a resistive component and an inductive component should be 90 degree to this. Okay, so this is my minus of I2 X2 and this will be the Where I have started the phasor diagram, I have started the phasor diagram from here and I am ending it here. So if I draw a line from here to here, this gives V2, vector V2. V2 is equal to E2 minus I2 R2 minus I2 X2. V2 is equal to E2 minus I2 R2 minus I2 X2. That is V2. Okay. Now here we have represented all the parameters I2, I2 X2 and V2. Now let us move towards the primary end. What is the KVL? If I apply KVL for primary side, V1 will be equal to I1 R1 plus E1 plus I1 R1 plus I1 X1. And here I1 is nothing but the current I1 is nothing but I0 plus I2 dash. What is I2 dash? This I2 dash is nothing but minus k times of I2, and this I0 is nothing but Im plus Ic. One is the magnetizing MMF or magnetizing component, and one more is the core loss component. Okay. Now first we need to find this I0, because from this I0 I will be getting I1, from this I1 I will be getting V1. Okay. So I0 is equal to Im plus Ic, right? This I0 is equal to Im plus Ic. And out of these two parameters, this MMF links with the flux. This MMF, magnetomotive force, links with the flux. So this is responsible for this flux phi. So what I am doing, I am writing this Im with in phase with flux phi. So Im will be in this phase. So this is my Im. Okay. So this is my Im. If Im is in this phase, then where I should write the resistor? It should be 90 degree to this. That is Ic. So I draw a 90 degree line, and this is my Ic. And if I take the resultant of these two, I will be getting I0. This is my I0, and this angle is nothing. This is alpha. Okay, so this is I0. Now I have written I0, I have got Ic, I have written it, Im, I have written it. Now next, how to represent this I2 dash? I2 dash is nothing but minus k times of I2, or k is a turns ratio, or I2 is I2 dash. That is I1 is the summation of I0 plus I2 dash. If I2 is flowing in this direction, then minus I2 should flow in this direction. If I2 is in this direction, then I2 will be in this direction. So what I do, I will shift the entire vector here, because this should be in combination with this, with I0. So what I do, I just write the vector here, and this is my I2 dash. Okay. So now if I add this point and this point, the resultant, this will be my I1. Okay. So I1 is nothing but I0 plus I2 dash. Now I got I1. Now let us move to this equation. So V1 is equal to E1. Where I should get E1? I2 dash I have written it. E1 will be in phase with E2 only, but the value of E1 will be lesser than E2. So what I will do, I will represent it here with a shorter distance, and this is my E1. So now to get the voltage, input voltage equation, what I will do, I will represent this E1 in the x-axis. Here I am just changing the magnitude, but the value remains the same, only the magnitude is changed here, and this is minus E1. Okay, magnitude I have changed it, but the value remains the same. Now I1 R1. Next is I have got E1 and I1 R1. If current I1 is in this direction, I1 R1 also should flow in the same direction, but this vector I will shift it to here. So this becomes my I1 R1. Next 90 degree to this. So this is my I1 X1 and this will be the resultant of this. Now the starting point of the phasor diagram is this and the ending point is this. If I join these two, then what I will be getting? If I join these two, now this is my V1. Okay, this is the starting point and this is the ending point. So this is how we write the phasor diagram. Now we have completed all the parameters E1, I1 X1, I1 R1, I1 and V1. So we have represented all the 15 parameters in the phasor diagram here. Thank you.